Sí. Bien. Aquí.
Hola. No, sí, con esto lo paso.
Well, start. It is a pleasure to introduce Professor Bernardo Uribe from Universidad de Norte. And he'll be speaking about equivariant unitary bordism and birational invariants of finite. Bernardo?
So, thank you for good afternoon. Ernesto, thank you very much for the invitation. Ludwig, thank you very much. This is a subject that I've been working lately, specifically in the side of equivariant Bordism. But recently, it has been come to many of us attention that this is related by some reasons that we don't completely understand to some birational invariants of finite groups. So I'll start first with the equivariant picture, or the Bordism picture, and then I'll bring some of the birational invariants that are related to this thing. And I will not cover all the birational invariants, but some of them. So since I see some, let me see, this is the first, yeah. So since I see some students, let me get the picture first, which is the Bordism question. So the idea is to understand manifolds, compact manifolds with different types of vector structures in them. It could be oriented, the unitary could be like whatever structure you want to put on them, but I will focus only on the unitary one. So we have a compact manifold, and we will say that it becomes stably unitary if one can add copies of the real space, and by adding it to the tangent bundle, then we may complexify this bundle. So this is like stably almost complex structure. And if we have an action of a finite group or a compact group, then we want, of course, that the whole thing is complex. So this doesn't mean that the manifold is complex itself. It just means that adding copies to the real, it will give us enough place to put a complex structure, an almost complex structure. And we say that two manifolds that are of this type are bordered if we might find a manifold of one dimension more. And you see, since we have this stable structure, it doesn't matter that the manifold is odd dimensional because we put this, we stabilize tangent bundle. If we find a manifold which is a dimension extra, on which the two are the boundary, one with some orientation and the other one with the opposite orientation. So simple picture, and I'm putting this picture because they may also live in a specific surroundings. So you have this boundary condition, but they may live in a specific space X. So if we just take these equivalence classes of manifolds with the specific decoration we want, unitary, oriented, non-oriented, and we just put them into a set that is called omega gn, and of course I'm using here, I'm always thinking that they have a unitary structure, but again, it could be oriented or just non-oriented or whichever decoration. Then you may do the disjoint union of these manifolds, and it gives an additive structure on that set, on the group, the Abelian group. But moreover, you can put all those groups for all possible dimensions, and then you get a graded group. But then we see that it's even more, it's a graded ring. So this object on the bottom, so we will be our equivariant Bordism groups. But as I said, it's more over a ring because you can just take two manifolds and the cross product manifolds. So it's a nice ring, but we should think, or the way I see it, it is a ring algebraically, but we should think that the generators are manifolds, manifolds in the hand. Now, the equivariant one is a module of the non-equivariant manifold. What do I mean about that? I have a manifold with an action, and I may have a manifold without any sort of action, and I could just do the product of the two manifolds and take the induced action of the group, and of course I have a bigger manifold with the G action. So the non-equivariant Bordism ring is acting over on the equivariant Bordism ring, and the non-equivariant is quite nice. And so far so good, but the idea of current is not just to define an algebra, it's to find the numerical invariant. So when is a manifold the boundary of another? That's the main question. When can I bound the manifold? So the idea is to calculate this object, not so much to define it. And so to calculate them, this is an idea of Tom that developed an idea of Bordism, which is to construct some sort of a space, universal space where the boundaries are happening, which is the Tom space. So how is this constructed? We simply use the universal principal UN bundle, and then you take the associated complex bundle to the universal one, which is the middle part there in the shortest sequence, that the fibers of the Riemannian, which is the classifying space of the unitary group. And the Tom theorem tells us that the homotopy groups, the homotopy groups of those spaces, which are called the Tom spaces, if you calculate the homotopy groups, that precisely is these groups that we defined before. Namely, you want to know of a specific dimension which manifolds bound or which ones do not bound, and of many of them, it's equivalent to calculate the homotopy groups of a specific space. These spaces are not trivial at all, but they do contain the information of the Bordism, and in some sense, in one side you have a Bordism, and in the other one you have a homotopy moving from 0 to 1. And so that's the way to do Bordism in one side and the other one a homotopy. So having said this, then it is a result of Milner and Novikov, more Novikov, let's say Milner and Novikov, that tells us that the Bordism ring, unitary Bordism ring, is a polynomial algebra in generators of dimension 2, 4, 6, etc. But it's a very nice algebra. These generators, if you allow them to be multiplied by a natural number, it could be taken as the projective spaces. So the projective spaces are multiples of the generators of the Bordism ring, but the generators themselves have explicit definitions. Milner has a very nice description of them, and Buchstaber now has a better one, but better. Historic manifolds. So they are very concrete manifolds that one can construct because one knows that one can know the Bordism classes to determine numbers. And so when, as I said, when the Bordisms live in a space, then we can take the Bordism groups equivariant living on a space, and this object, this group there, becomes a generalized homology theory. It's proven by Atiyah and later by other people. So these groups that I put there is a homology, a generalized homology, universal homology in some sense for complex-oriented classes. And so the idea of the question is, let me just go back. So in some sense, if you just have a manifold and you don't have any group acting on them, and you want to know what its unitary Bordism class, you have to fit it into this ring there. And to know where it lies, you just calculate the Chern numbers. And with the whole array of Chern numbers, you know exactly where it lies, and you can say what is the Bordism. So in that sense, it's a closed problem. You give me the manifold, you don't give me the manifold. You get your own manifold, you calculate the Chern numbers, and then I can tell you where it lies. And so, but the thing is, we want to somehow do the same thing whenever we have a group. Now, this group somehow rigidifies the problem quite a bit, and not everything is possible. And one could think that it's the same type of problem that should be done the same way. So how is the same way? The same way is, well, to construct some universal, some homotopy universe where all the Bordisms are happening, and then instead of calculating the manifolds here, calculate their some homotopy groups. Well, easier said than done, because this universal construction, which was done by Tom Dick in the 70s, and mimics the universal construction in the non-equivariant case. But whenever one does transversal intersection, which one does in the case of the non-equivariant case, one can do it. You just put enough dimensions that you can just transversally intersect manifolds. But whenever you have a group, the group blocks some sort of transversal intersection, because you cannot somehow get away fixed points of certain elements of the group. So even if you want, you cannot do transversal intersection if you don't have enough room to do transversal intersection, but not enough room outside of the concept. You need to have enough room in all possible fixed concepts. So you need to somehow stabilize all over the place, at least stabilization all over the place, break somehow the relation that we had before. Before we had the homotopy groups of some spaces, exactly the same as the Bordism groups. But as I said, so there is a generalization due to Tom Dick, and then one can define a spectrum. So at least the second word of the three themes of this conference, spectra. So there's spectrum, and there are two spectrums, so there's spectra. So there is which is called MU spectra, equivariant. It gives me a generalized equivariant homology theory. And the problem is with this equivariant homology theory is that we don't have an isomorphism anymore. So that means that the left-hand side is omega, which is geometrical Bordism. You imagine a manifold and a manifold, equivariant Bordism. On the left-hand side, but of course maps to something on the right-hand side, but in general, is not known whether it's injective or subjective. Basically, not. The only thing we know is a homomorphism. Meanwhile, you take the G away, well, precisely, it's an isomorphism. So, of course, this is good and bad. You may think of it either way. And in some sense, the left-hand side, we're doing non-stable geometry. Maybe you're stuck with your manifold in the dimensions that you're stuck with.
G is not only, of course, spectrum. It's a G spectrum, right?
Which one?
MUG.
MUG is a G spectrum. It's not even
So this, you don't know this as a spectrum or as a Tanakian spectrum.
You don't know as any spectrum, because the left-hand side is a not stable one, and the right-hand side is a stable one. So either one, I don't know
But
which.
I think maybe an statement with Tanakian spectrum could be useful for solution. I don't know.
I don't know. The only thing, what I know is that the left-hand side, you are not allowed to stabilize, and the right-hand side, you stabilize, and it's quite easy to construct classes.
No, because of the Thomas.
I don't know why you
Well, the thing that, of course, on this side, you don't have the Thomas isomorphism. You have the.
In the left-hand side,
you don't do the form contrarian.
well, in the left-hand side, of course, not. You just have one. In the right-hand side,
But when you do the right story,
yeah, you derive, then you're on the right-hand side.
you don't see it as spectrum, but just like a Tanakian spectrum, maybe there is that kind of foundation.
So yeah, I don't know. Maybe there's a middle step, but I don't think there is a way to overcome the difficulty in the spectrum on the left. There's no way, because the one on the left has, you don't have any.
As it is.
As it is, no. So the first is, what is the question you want to answer? Is it the homotopical one, which is a specific question, or the geometrical one, which is another question? Both are interesting, and both matter at some point. Let's think of it. One is stable, the other one is not stable. But the problem is with both sides is that they're difficult to calculate. Both sides. So we're somehow stuck. But here this construction simply says that if you have a representation which is faithful, then one can construct on the homotopical side, one can construct classes that are living in negative gradings. And because they're living in negative gradings, they are not going to leave the geometrical side. So this is the order classes. Of course, the dual of these ones live in the left. So in some sense, the right-hand side has more classes. You You're allowing to invert some classes, which on the left you're not allowed to invert. But nevertheless, it's difficult to calculate either side. So this was somehow studied in the 70s, right after somehow the Altilla and Quillen studied the non-equivariant case, and somehow there was I would say enough developments to think that it was something that it was calculable, and many things were done for abelian. So whenever you have an abelian action, many things work well and diagonalized, and you can just do some sort of induction on the cyclic parts of the group, and you can just, since there are abelian, you can do a lot of numerical constructions. And it turned out that whenever these groups are abelian, and you want to know what is this equivariant Bordism group as a module of the polynomial algebra of the non-equivariant case, well, it turned out that they were always generated in even dimensions, and they were always a free module over the polynomial algebra. Namely, in geometrical terms, there is no torsion anywhere, and all the odd-dimensional manifolds bound. That's what it says. All the odd-dimensional manifolds equivariantly bound, and there is no torsion class. And so it was somehow pushed a little bit forward by metacyclic groups, but not so much, not any non-abelian group of any interesting type. And at the time, it was.
Sorry.
Yes.
So you took a great care of the exam, but the name is Lazare of Lazaro.
I didn't tell me Lazare, not Lazaro. I apologize. Okay. And so at the time, it was written that it was expected that the whole equivariant Bordism group would be a free module over the polynomial algebra given by the non-equivariant Bordism ring. But somehow this somehow was written as a hope, no? As hope that it would be the case, and many years passed, and people rewrote it and wrote and rewrote it because it doesn't follow from general constructions. How it depends on calculations, and the calculations are difficult, are still difficult. So it was in the 80s, then it was getting in the 1996, the same conjecture, it should be the case. 1997, people started getting maybe false, but still, yeah, without any concrete example to show that it was false or true. I just somehow started looking at this problem, and Landweber was happy, he's still alive. He was happy that some of his work in the 1970s was retaken by a new group of people. And somehow the idea is the following. So you have a representation of a company group, it's finite for the case being, you have a representation of a finite group, you know that if you know the character of the representation, you know the representation. So that is basically saying there is no torsion in this type of representations, and if you just go and look at the fixed point data, you know what it is. You can just go back and construct it. This is at the level of equivariant homology theories is go and look at the fixed point data. And if in good cases, the fixed point data information tells you everything about your object in the video. And of course, I'm talking here about homology. No? So on the left-hand side, I have the homology, equivariant homology. And what I will do, what I'm putting up there is that take any finite subgroup, localize, so take the fixed point data of that. So you have a manifold with a group action, take a subgroup, take the fixed point data as a manifold, take the normal bundle around those fixed point data, that is a bundle that has representation, split the representations on the superficial classes, and you have two sort of bundles. These bundles are classified by maps to some Riemannians. And all this map on the top says if you have some sort of a manifold there, you get some sort of Bordism classes of Prismatic. So manifold in Bordism. As I said, it's just the normal bundle of your fixed point data. And if you do that for all finite subgroups, of course, in the conjugacy class, if two groups are conjugate, the information is equivalent, then you may build a map. Take a manifold, all the possible subgroups, conjugation, take the fixed point data, normal bundle, classify the normal bundle with a map to the Bernstein, and you have a map. And if you're lucky enough that this map is injected, then of course you can recover the information of your equivariant group from the fixed point data, as in the representation. You have a representation, take the fixed point data, which is the trace of the elements of the group, and then you can recover the representation. But that's the whole. And if we take another homology theory that is equivariant like K theory, where K theory is just a generalization of this representation here that I just told you, that's the case. You can reconstruct the K theory element from the K theory of the fixed point data. And that somehow one could imagine, okay, that would be the case for any homology theory. Now, if we tensor with the rationals, then all this torsion information is lost, and it turns out that you can recover all the non-torsion information from the fixed point data. So it's not a free problem in some sense. The problem is, what is the torsion? Do you have any torsion on the left-hand side or not? Because if you don't care about the torsion, everything is localized in the fixed point data. For any homology theory, if it has certain nice properties, it's a certain nice functor of homology. So, but let's imagine that we have the case that is that these equivariant Bordism groups are indeed a free module.
So even this conjecture originally places HKR or
The original place of the conjecture is Bordism.
no, what I mean is in the HKR paper or where?
Is there hidden in Landweber's in the document behind in a sentence, and then somebody else took it, and then Peter May took it. But I will show the HQR. So, but if the Bordism group is a free module over the polynomial algebra, then there is no portion, there is no integral portion. And if we take the homology of BG, which is, let's just think that this homology of BG is telling me the Bordism of BG is telling me the Bordism of manifolds with free actions, the principle of G1. So imagine find a group, free actions, and you only consider free actions with Bordism also being free actions, and that's the left-hand side. But we know the homology of BG is called torsion, so there are plenty of torsion elements on the left. And if I take these torsion elements and I map it to this non-torsion group, then they have to vanish. So geometrically it's telling me if this is a free thing on the right, any manifold with a free action, any manifold with a free action should bound equivariant, not as a free manifold, but should bound equivariant. So the unionist conjecture would imply something that one can check whether this is true or not. And of course, again, the way that it was proven that that's the case, was this manifold bound is case by case. Basically, you have to construct generators for the manifolds in which you have actions. You have to really construct usually with length spaces and whatnot. But quite recently, so some counterexamples started to pop up. And so this idea was taken by a former student of Ernesto in Mexico, and he wanted to answer the following simpler question, which is already important enough. Take a finite group, take a surface, compact oriented, forget about the unitary structure, just compact oriented surface with a finite group action that is free. Question, does it bound equivariant? Can you fill it equivariant? And it turned out that Carlos, with a student, showed indeed with some procedures that he learned when he was a student of Ernesto that he can fill it if the group is dihedral, symmetric, abelian, some non-abelian groups. But when he put the paper on the archives, another person that is Eric Samperton was working in low-dimensional topology, and he had a construction of some surface with a free action that would not bound. And so he noticed his paper, and then we started talking to him. And the point is that he noticed that there was an obstruction to fill a surface with a free action. And the obstruction lives in something that is a version of some object in algebraic geometry, which is called the Bogomolov multiplier. But I'll tell us in a second what it is. So this is just letters what I put there, but the middle term is the Bordism group of free actions. The middle term of the shortest sequence. Namely, think about surfaces with free actions. And the left term is telling me take three-dimensional boundary on which the boundary has to have a free action, but internally it could be anything. And this would be the image of the map would be the free actions that bound. And so if you take the co-kernel is exactly what we want. Are there manifolds which do not bound? And the result is of Eric at the time is that if the group is of odd order, to get rid of the Platonic groups, if the group is of odd order, the obstruction for the filling is given by an object living in the second homology divided the toral classes. And this group that you see there, it is the homological version of a group that is called the Bogomolov multiplier in algebraic geometry. In algebraic geometry is a homological, but it's the same sort of object. Namely, any manifold that you can fill has to have some sort of, has to be of toral class, has to be a bunch of toral going together. It cannot have any higher genus. And of course, once you do this, one would like to see what are examples of that. But when we took that result and we brought it to the Bordism question, we will manage to generalize it to any finite group, not only of one order. And we noticed that the equivariant Bordism group, well, has torsion. Has torsion even at level 2. We don't know the higher levels we expect. There's a lot of torsion, and the torsion is precisely these Bogomolov groups. Once, of course, you take the conjugacy class and whatnot. But there's this thing that there is a lot of torsion in these groups, so this conjecture is not true, but we need to somehow be careful about the groups that have distortion. So this is the smallest group that has whose Bogomolov is non-zero. And there are two other of this size, but they are isoclinic, namely they are related by a certain way in which they give the same construction. You see, well, it looks easy in some sense because it's just the quaternion is acting on a cyclic group, but it's not that easy somehow if you want to see what type of elements, or if you want to generate a second homology with torus, you notice that you cannot do it precisely.
And this, of course, is also conversion to Nether's problem.
Yes, of course. I didn't say it, but that's the algebraic universe, of course. This is also a group that contradicts, or not contradicts, that is, that's a example of not responding with respect to rationality of G acting on a faithful representation and the coordinates. Good. So, as you may see, something to do with if you want to generate second homology, you need a genus 2 sort, not generated in one. And the obstruction is this group. Good. So there are groups on which this Bogomolov is not zero. Bogomolov himself many years ago showed that there are groups of order P to the 9, and now there are people working to construct or to detect this type of obstruction. And so this conjecture that was put several years ago, of course, is false. Now, that's not the question now, being false or right, is for which groups then the equivariant Bordism groups is a free model. That's more the question, for which groups not. And moreover, where are the torsion classes, or what are the elements of dimension, of odd dimension? But just to continue, this is something that appears not only in Bordism, it has appeared in other homology theories. So,
Moravaki theory.
X like Moravaki theory. So we need to consider, of course, homology theories with a little extra story. These are homology theories which are complex oriented. Namely, that they have some sort of a hop bundle inside. Namely, that it has a class in the second cohomology of the infinite projective space that behaves like the hop bundle. And the main examples of this is these three homology theories: Bordism, Brown-Peterson cohomology, and Moravaki theories. So Brown-Peterson cohomology is a multi version of Bordism, and Moravaki theory is getting a structural piece, a smaller piece of the Brown-Peterson cohomology. And you may see somehow here the Brown-Peterson cohomology, which is localized at the prime P. It has also generators, a pre-Symmetric algebra, but we're picking up certain generators of the Bordism ring. Not all, some, of course, it's infinite, but we're picking some. And it was already proven by Landwehr many years ago that if you calculate the Brown-Peterson cohomology of a product of a billion groups, it's just the product of the Brown-Peterson cohomology of each couple. Unlike the cohomology of CP cross CP, which is not the product of cohomologies. So namely, these cohomology theories are well behaved in respect to product of groups, as you may see here, and it's somehow not easy, but possible to do a specific formula of how these rings are. In the case of Moravsky theory, it's a smaller one. It has only two generators, the cohomology ring, so it's more manageable. And this Moravsky theory, there is a very nice Kuhn isomorphism, unlike in other cohomology theories. And it was also proven by it wasn't Landwehr, but later on, that also it splits the cohomology of the product of the groups in this algebra, and of course it's telling us that it's behaving well and living in the proper dimensions, and that there is no torsion, and that everything somehow looks well. And so the evidence conjecture in Bordism has some sort of also appearances in the other cohomology theories, and there are somehow positive constructions, positive evidence conjecture for some groups, negative for some other groups. It is not yet clear what is exactly that makes a group to have free equivariant Bordism groups, or free Brown-Peterson cohomology groups, or free Moravsky theory groups. But somehow the idea is similar. It's quite similar. So Igor Chris in 1991 constructed some counterexample for the evidence conjecture in Moravsky theory. His daughter used it to construct a counterexample in the homotopical unitary equivariant K theory. In the Brown-Peterson, of course, if one is smart enough, one can show that it's also a counterexample for the Brown-Peterson homology. And there's some sort of principle behind this equivariant homology theories calculation, which is if we somehow in these equivariant homology theories we disregard or we don't care about the torsion elements, then everything is localized in a billion subgroup, which is what is called what is this theorem? Anyway, so you can see there we have a generalized cohomology theory, and we may somehow restrict the information to a billion subgroup, and we may put all the billion subgroups, and if we invert the size of the group, then everything is detected by the billion subgroups. So if we don't care too much about the torsion classes, you may just restrict to all a billion subgroups, and then it will detect the information. And so because of this structure, it was a result by Hopkins Conrabanel on Moravsky theory, then that one could somehow calculate the Euler, or the rank, or the Euler characteristic of the Moravsky theory with spanning space of finite groups by localizing the information in these abelian subgroups, which could be thought as commuting tuples. So if you are at level n in Moravsky theory, you need n elements of the group that are pairwise commuting, and if you count those pairwise commuting tuples, then it turns out that size is exactly the rank of the the graded rank of the Moravsky theory, basically telling us what is the size of the group itself. But of course, this is disregarding any torsion whatsoever. So then they at the time said, well, it may be the case that the Moravsky theory of any finite group is again concentrated in even dimensional generators in this free module, and they made it as a conjecture. And they were good enough at putting what are the conditions on a group so that I get this result. They call these groups good, and good means that you get a good transfer map from a subgroup to a group using Euler classes from the representation, from the huge representation. And it says a group is good if the equivariant theory is spanned by good elements, and good elements mean that they come from transfer maps. So basically, you can get the information from the group, from its subgroups. which one thing that might be always the case if you're thinking of representation. And if the group is good, then the Morava case theory, the classifying space is concentrated in a dimension and string. And this was shown for a list of groups by several people in the 90s until 1991, that it Chris showed, oops, there is a counterexample. There is a group of size, if I don't recall, is P to the 6th, which is a P-Silo subgroup of this generalized linear group, on which no, it's not true. There is some odd dimensional elements in this Morava theory group, and it somehow destroyed the conjecture of Hopkins-Constantman that they thought all the groups are good. So it's another appearance of the same phenomenon that is telling me there are some groups that are giving me interesting information in the homology theory. And so there was the homotopical version of this conjecture, and the daughter of Igor Chris showed that it's not the case, because she took the case of the construction of her father and pushed it all the way to the Bordism, and it's not true. So it's another group. This other group, the Bogomolov multiplier of this group is 0. So it's not the same as before, it's another type of obstruction. And what I want to somehow show now that so we have Bordism, we have Brown-Fitton homology, we have Morava theory, they all have some glimpses of cases in which there are groups which have torsion classes with homology, or which the generators appears in odd dimensions. And I want to show you some more appearance of this Bogomolov group, which is the torsion part of the Bordism green, that appears in something called cut and paste homology, Schneider and Clayton in 1970s. Matthias Craig and Bonn and his students constructed a homology theory out of, you take a manifold and you cut it in such a way that you may glue it using the boundaries in a different way. And then you say these two manifolds, the first one and the second one, which just cut it and put it in a different way, they are in the same equivalence class, and they define the homology theory. This homology theory, they denoted Schneider and Clevin, on which if you take the reduced groups, you may think of it as a manifold divided over equivalence relations. The Schneider and Clevin groups of the classifying space of a group and the surface case, they calculated at the time, they didn't call it Bogomolov multiplier, they called it second homology divided total classes, and there was already an appearance of this group in the 1970s, but they didn't push this homology forward. And now, the Bogomolov multiplier doesn't appear as an object in the right point, it appears as an object in birational geometry. So this is a construction due to Fedor Bogomolov. Ludmila might correct me if I'm not saying it correctly. Fyodor Bogomolov, which is that there is something that is called the unramified Brauer group on the right variety, which is a birational invariant of the algebraic variety. Bogomolov gave an explicit construction of how to calculate the non-ramified Brauer group of the variety constructed by a faithful representation and an action of D on this faithful representation. So, and it turns out that if you take a resolution of the variety, good projective resolution, and you take the third homology, you take the torsion part, that's exactly what it is. And he explicitly showed that this unramified Brauer group is the same as the element of the Schur multiplier that vanish on all abelian subgroups. Okay, this is the Schur multiplier, this is the second homology of the group with coefficients in the units of the complex group, and take the one that vanish on all abelian subgroups. And with this construction at hand, he himself could construct several examples on which the unramified Brauer group is not 0, therefore constructing non-rational varieties out of a group and a faithful representation. But they also appear in another disguise, in another construction, and over there it says conservation scientific ring. It's just somehow covered by this thing, and it will be hopefully related to what Enrique will explain, but I don't know if Enrique will explain the same thing. I will just simply go a little bit quick over this construction, which is the Grothendieck group of varieties, on which we want to somehow, this is my appreciation of it, we want to somehow control the birational classes. So we want to do that. We will somehow split. We have a subvariety Z over X. We will construct this group of which we simply allow to say that X is the sum of X minus the subvariety plus number alert. So what happens? Oh, sorry. Yeah, the telephone line. No, it's a number alert.
One has code in history.
So, I don't know. It's a China adoption. What happened?
Different children. Different children in only in the US.
In the US.
In the US. There was a kidnapping in Bangladesh.
So people in. So sorry, what was just my telephone? No, it's just. So
What's close to
so then we might construct these Grothendieck varieties by taking all possible varieties and taking this equivalence relation to define it, and it of course becomes a ring, the same thing as in the Bordism ring, that you just simply put the product, and then there is the specific elements which are given by the affine planes, and if you can with this relation you can see that the projective space is just the sum of these affine lines by the way the cells, the projective space is constructed.
How is the product of two subvarieties of X subvariety?
How is the product of two subvarieties
Of X.
of X?
A subvariety of X.
I don't know, but you keep it stratifying, because when you take your subvariety, you put them up, and that's another subvariety, and then you just have this one, You keep doing this. If you're thinking of two that they cross, the subvarieties, so then you stratify this against by the intersection. You keep splitting them in pieces. It's an answer. It's not the product, but it's otherwise. You have to summarize.
You fix a variety.
No, you don't fix any variety. It's a whole variety.
So those varieties of what?
Z is a closed variety of X.
Yeah, but
If you take an X, and as long as you have some variety, you put a relation. If you discover that Y is another variety, you put another relation. Okay.
and there's nothing to do with the product.
Yeah, it has nothing to do with the product. Product is another letter. For any subvariety, put all subvarieties you add relations to these objects. So you put all varieties, and then you start putting relations. The relations are given by any variety and subvariety, and that's what it is.
You're calling them.
Start calling them. But the good thing is that this is generated by blow-ups, no? In the smooth proper varieties, and so we can take our smooth our resolutions of the varieties are smooth, and then we take the exceptional divisor, and then we can take those differences, the blow-up and the exceptional divisor as an array. This relation. We can do it all smooth and then the divisor. And I'm not doing this an amazing way, I know. Enrique will do it in a very way, perhaps. But then we complete it appropriately, and we divide by the alpha line, and these are going to be our civic ring, essentially. But of course, we want to have invariant of this object. This object is wild, it's gigantic. We want to get some invariant. And one of the invariants is the cohomology gamma, namely giving the cohomology of this object. And we put, of course, some decorations to keep track of the dimension of the cohomology, but simply is take what lives on the right hand side is the appropriate object to keep track of all the cohomologies in with keep track with the coefficients, and the idea now is to see how we can put a finite group in it. So the way to put a finite group in it is to take a group, to take a phase representation, and to stabilize the representation by adding it several times. And then you see here on the bottom that you have the representation. You add it n times, but then you just control this the dimension of that by dividing by the appropriate alpha line. And if you take the appropriate limit, this is a way to see that it's the BG, the classifying space version of this object, which is not the homotopical PG, but it's similar in nature to the homotopical PG. And in this way, we can define this cohomological invariant associated to a group, which is simply the cohomology associated to this to the variety, or to whatever resolution you may like of this variety. Now, then with this, and I didn't know him, so I don't know. Ekedal defined something that he didn't call it ekedal invariance, but because he was the one defining them, what is called now the ekedal invariance associated to a group. I think right, and so we have our quotient space, and we take our proper smooth resolution, and stabilizing properly, we may define ekedal invariance for a finite group for any number. And it's exactly when I put this in brackets means that we remember the abelian group that they are. So you should think that this is just abelian groups that we're putting there. And of course, there's some leading terms and there's some low dimensional terms that they all appear in the invariance. So this is a theorem of Ekedal already. This is 10 years ago, 15 years ago. And the negative invariants are all zero. The zero invariant is the integers. The one dimensional invariant is zero. And the first somehow interesting invariant is the second Ekedal invariant. You should think there is some sort of a dual thing in homology when you define correct dual in the appropriate version. But anyway, so the point is that the second Ekedal invariant is precisely the Bogomolov multiplier associated to the unramified product. And there are the higher invariants, and Enrique might correct me, are not known. The third, fourth, fifth, one. Somebody has to calculate at least one soon, but they are not known. So, but the point is that, of course, these invariants are not trivial. Provides an obstruction for rationality because if you put rational variety there, the invariants are all zero because this is calculated they are all zero. So whenever you just get an invariant here that is not zero, then you have a rational invariant of the variety. And what is of course interesting is that the same object is appearing as in the Bordism question. Again, and you can see the same difficulty in some sense in the topological side. We are only at level 2. Why? Because we don't know the rest. In the algebraic side, we are level 2. Or they are why? Because it's difficult. We don't know the rest. We have been able to calculate this the most small dimensions. And so in that universe, there are also calculations for when the invariants are all trivial. And these are, it's not a complete list because I don't know the whole total of the list, but this is at least what I found. For all these groups, all the invariants are trivial. But that doesn't mean that we know when the invariants are non-trivial. And
no examples
well, we know examples, of course, we know many because we know the Bogomolov, which is the second level, but we don't know when the third level, or fourth level, the fifth level, sixth level, third level, and so somehow that is still missing also in this universe. So there is a just to finish. There is another that I didn't have time to put it, but there's another invariant that is the unramified generalized groups. That is the one I just showed is at level 2, but there is a way to non-trivial and very smart way to generalize those unramified objects to higher levels. And again, those ones haven't been calculated for higher degrees, and there is some formula for the third degree that already is something new. But the point, and just to finish, is that it is somehow the same question. It's somehow the same question in different universes, which is in one is do your manifold with reaction bound. In the other side, you have an algebraic variety on which there is an open set on which the action is free. And then you need to just take some resolution of some kind, and then you want to see whether that's rational or not, and which interestingly so, they are similar invariants controlling the two questions. And of course, one can imagine that it's very similar.
The important part of that is complement.
That's true. That's what Ludwig said. So how do you control the complement of this free part? It's exactly where the information is lying, and this is the information that is also equivariant, because of course in this complement the action may not, of course, it's not free, but some parts are free, and there's some divisors in some sense, in the equivariant sense, and the algebraic sense, in the topological sense, it's again some top manifold with an action. So what is behind is somehow to understand manifolds with actions and all its normal bundles around it. Because the normal bundles are the ones that we were saying what is controlling the complement of the free part. And even though we have some sort of the objects that could control this non-rationality, and on the other hand, we have the object that could tell us which objects bound or not, and the explicit calculations of the object are not yet done. These are, in each case, complicated. And each case has a list of groups on which everything works and some contradictions in each. But of course, there must be some sort of connection, clear connection from one side to the other and vice versa that would allow to detect information in the right context to the topological one and vice versa. And I suppose it's related somewhat to what Enrique will say in the next talk. But
So are these SK groups